Adelante.
Okay.
So it is 8 o'clock, so we can wait like 5 minutes.
Yes.
Yes.
Disculpen, ¿se escucha bien mi audio? Es que yo también estoy teniendo problemas con el internet.
Se oye bien.
¿Se escucha bien?
Sí.
Yes. Perfect.
Sí, yo tenía la misma pregunta. ¿Puedo apagar mi cámara cuando la presentación?
Yes.
Gabriel,
Sí.
I guess it's almost time.
So
we are waiting for a couple minutes more.
It's because we have only 6 spectators.
Six. Okay.
So
Okay.
I was just waiting 5 minutes after.
Mexican style.
Yes, exactly.
No, don't say that.
Oh, sorry.
So 2 minutes or 3 minutes. In 3 minutes we start. Is that okay?
Yes, very okay.
Okay, so probably we can start, right? Because we are consuming precious time of your presentation, Roxana.
Don't worry. Okay, we can start. Right.
Let me just welcome everyone to this last day of the International Conference of Science and Technology of Complex Fluids, so long name. So today we have Roxana del Castillo from National University of Mexico, and she's going to talk about electronic transport properties of graphene polymer nanocomposites. So please welcome Roxana.
Thank you very much. Good day. My name is Roxana, as already mentioned. I will talk about electronic transport properties of graphene nanocomposites. I made this work with Jorge Luis Apátiga, a student of mine, Luis Felipe del Castillo of the Material Research Institute of NAM, Alipio Calles of the School of Science, and Vicente Compain of Polytechnic University of Valencia. Well, first, I want to present my research group in the interdisciplinary laboratory. We are 3 professors, Alipio Calles, Raúl Espejel, and me, and several students. Well, for pandemic issues, I have this photograph, but I hope to get soon an actualized picture. Well, the main purpose of the laboratory is to use all the tools available as experimental, theoretical, or computational tools to solve research problems of basic science or applied science. Also, we are interested in fostering dynamic process of knowledge generation to solve problems important to humanity as pollutants in the atmosphere of water. My main role in the laboratory is to use the computational tools to get solved all problems, all these kind of problems. Imagine. The research line of our laboratory are in the topics of computational physics, electromagnetic phenomena, dynamic capture and conversion of greenhouse gases of all and other pollutants in the atmosphere, polymer graphene nanocomposites, and in general, bidimensional materials. In particular, this talk is going to be about concerns polymer graphene nanocomposites, but right now I'm working in silicon to apply application for high performance broadband photodetectors. Well, as you can see, we have several issues in mind. In general, it is well known that graphene in small quantities, graphene nanoparticles in small quantities, modify drastically the electronic and thermal behavior. This phenomenon can be well understood by the stochastic theory, and it is known as percolation theory. So we are going to use these tools, these mathematical tools, to study this problem. So in classical percolation theory, to transport electrons from one lead to another lead, for example, from this part to this other part, it is necessary to create a path. In this case, the path would be created by graphene nanoparticles. Here, as you can see, there is then graphene nanoparticles, and when the nanoparticles are clustered or clustering in the polymer, they create this path to transport the electrons. If we made the classical percolation theory and we made the calculations to obtain the transition probabilities to transport the electrons, and the assumptions are only geometric ones, only classical, we are going to obtain that we need 50% of graphene nanoparticles to obtain an efficient electron transport. But as the graphene nanoparticles have quantum effects like pp stacking or dispersion correction effects, or van der Waals forces, the graphene percentage is drastically diminished to obtain a good electronic transport. If we draw the plot of fillers content versus the transport properties, as transport properties, we can study electronic conductivity or even thermal conductivity. The characterized curve is described by this sigmoid curve, as you can see here, with this shape. So in this point, in the blue points, the transport properties, it's very low. It's bad behavior of the transport properties. For example, if we have a low filler content on the polymer, we have a low, for example, conductivity, electronic conductivity. But as we reach the yellow arrow, the behavior changed drastically. And this drastically behavior change as they improve the transport properties. Here comes a better good behavior. So what is going on here in this critical point? Well, there is a path in which the electrons can be transported. This is the main important thing here. This critical point is often called percolation threshold in this percolation theory. And I'm going to use this percolation theory to call it the critical point from now on gone. Well, for transport properties, there is very good the behavior of these nanofillers, modified excellent the polymer and improve. But regard to the mechanical properties, unfortunately, the tensile, for example, the tensile versus model Young's is not so well behaved. The Young's model is well improved for polymer, but not so good to reach graphene's Young's model. I forgot to say, when we have transport properties, we already reach conductivity as graphene pure, which is very important for industrial applications. But for mechanical purpose, for mechanical properties, this is not so good. So this could be an area of opportunity, a chance to improve this material, and for an industrial point of view, maybe can be an Achilles heel to improve the mechanical properties of these nanocomposites. While continuing with the mechanical properties and all the issues to solve is the saturation. The saturation do not behave as the common stochastic theory predict. For example, for electronic conductivity, the saturation is well behaved, and as I already mentioned, is described by the Boltzmann sigmoid. But as we are talking about mechanical properties, this sigmoid is not already well description, and the saturation is weird. Even though, for example, Young's model had saturation not well described, strength elongation at breaks, as you can see, they do not have this well-behaved sigmoid percolation, and maybe the saturation process do not complete. So we have to study more about it. It's all, as I already mentioned, things to think about in future. Well, a little of motivation of a study, of keep studying these nanocomposites, besides all the bad points that I already mentioned with the mechanical properties. Well, is the huge number of applications that this material have. For example, for liquid crystal devices as interface of the devices, for example, organic light emitting diodes, for example, solar cells, sensors. They are perfect for sensors or of temperature, pH, or CO2. For energy storage, supercapacitors, or even biomedical application as drugs or gene delivers or artificial muscles. With respect to the supercapacitors, the interface is going to be a sandwich of the capacitor in which the polymer is like a substrate, graphene, then graphene and polymer. So the supercapacitors are thing with this geometry. Okay. The experimental method of this work. The experimental method of this work was made in Valence by Professor Compagne and was by demand of a Swiss company. I don't remember the name, I apologize. But this company demand the calculations and the experimental because they are very interested in these nanocomposites, in particular in polypropylene with graphene nanoparticles. The nanocomposites with very were made with different percentage of graphene and was obtained with this copper-ion co-rotating twin screw extruder with a diameter, well with these longs, with these dimensions. The samples dimensions were 10 by 1 by 0.4 centimeters. And the nanocomposites were prepared with a percent of 0.5, 1, 3, 5, 10, 15, 20, 25, and 30 with nanofillers. The nanofillers were incorporated via a master batch under the conditions of 60 revolutions per minute and a temperature profile around 200 degrees. 200 degrees. Sorry for the imprecision of the experimental method. I hardly understand all the procedure very well. As far I understand, Professor Compagne took a polymer substrate and heated, and then when the polymer is liquid, he put the nanoparticles as desired, controlling the quantity of the nanoparticles. Then he mixed at high velocities, maybe with the extruded. And then he put it in a mold or a matrix and get cold with the nanoparticles in theory in a random position. I said in theory because it's not random, pure random, is because they had these interactions, these quantum interactions between the nanoparticles. These are the same image of all the samples. Well, here is a sample for 5% of the graphene nanoparticles. Then after the samples were made, electrochemical impedance spectroscopy measurements were carried out for all the samples. The electrochemical impedance were made at different temperatures from 20 to 60 degrees. The main advantage of made the electrochemical impedance spectroscopy is that we could obtain direct the impedance and the angle phase here, for example, and then obtain with an indirect equation and indirect relation the permittivity and the conductivity, which is what we interest in the conductivity. We obtain these Bode diagrams. In the electrochemical impedance spectroscopy, we can obtain the Bode diagrams or Nyquist diagrams, but we think that Bode diagrams are more clear and give us all the information that we need. Here are our Bode diagrams. As you can see, for our experiments, as I already mentioned, here there are several things to a point. For example, data for the real part of the conductivity were analyzed in terms of the corresponding Bode diagram. where variation of the conductivity with the frequency of all the samples are shown here. Here are the frequency and the conductivity. This plot is shown as double logarithm plot of the conductivity versus frequency and logarithmic, both. Similar behaviors here are for 50 degrees, but for other temperatures, we observe similar behaviors. So we only represent one. A close inspection of the figure shows that the real part of the conductivity of the samples in the range of 20 to 30 percentage of graphene nanoparticles, which are here, presents a plateau, a slope of 0. Actually, the phase angle is 0 as a slope, which represent that the imaginary part of the impedance will be 0. And this is behavior characteristic from conductors materials in which we only have DC conductivity. For the others percentage, we have the dielectric behavior characteristic with a phase angle or a slope different from 0. As we are increasing the frequency, the conductivity is increasing as we expected for a dielectric material, which is characteristic for polymers. And in this region, when we have the phase angle change, we can set that we have the percolation threshold or the critical point, which is what we are going to study in a deeply way. This information is exactly as the Nyquist plots. Well, respect to the computational method, the calculation have been made with Quantum Espresso computational package. We made several calculations. This Quantum Espresso code use plane wave set and pseudo potentials. We perform the calculations using density functional theory, DFT. And we use generalized gradient approximation, GGI, and the Purdue-Burick-Herzenhorst parametrization, PBE. Common sham orbitals were expanded in a plane wave basis set up to a kinetic energy cutoff of 40 Rydbergs. In order to relate the computational simulation with the experimental part, we use different monomers with 1, 5, and 10 slabs. One slab represents 30% of the fillers in the polymer, and 10 slabs represent 1% of the fillers. We extrapolate these calculations with the different numbers of monomers, sorry, with other kind of polymers. We choose polymers popular in industry and in general, not popular in general. For example, PS, PET, PEG, PP, well, polypropylene, and polyurethane. At the beginning of the calculations, we perform a systematic search of the ground state configuration, putting all the polymer monomers over a graphene nanoparticle or graphene side nanoparticle in different positions, and we search which one was the ground state configuration. We use several configuration of this, and the results here are the results. Okay. The results were agree with experimental evidence, in which we saw that the ground state configurations were placed in a parallel position, indicating that the graphene clusters clusterize over the polymer in a parallel position. So the graphene have the tendency of to form second layer over the polymer. So this is one of the results obtained in this work. Here are the adsorption energies, the adsorption sites, the bond length, and we obtain the HOMO-LUMO gap. Well, from the HOMO-LUMO gap and the ground states configuration, we observe that we have two main behaviors. The first behavior is for polymers with aromatic rings. The aromatic rings tend to stacking in a AA stacking over the polymer, which means that the rings are the carbon of the ring from polymer and the ring from carbon graphene are placed right up to one another, right? So and the other behavior, it would be seen here in D and E figures, in which we have linear polymers, and the CH, the carbon and hydrogen, are stacking over the graphene rings. Well, with this kind of behavior and the energies and the gaps, we conclude that these two behaviors are, in fact, for the polymer with rings, a PP stacking, which it was expected from literature, that it was reported that these nanocomposites have PP stacking, van der Waals forces, electrostatic interaction, or more strong chemical bonding. But we observe, in addition to things observed in literature, that there is another stacking, a CH/P stacking for linear polymers, which are here. Also, in this separation of the behaviors, in the PP stacking and the CH/P stacking, we observe that for the PP stacking, the HOMO-LUMO gap is minor, is relatively low, as we can see, very in agree with the conductor material. For other hand, the linear behavior, the linear polymers have in the CH/P stacking have HOMO-LUMO gap of 0.9 electron volts, almost the same gap for the two polymers, polypropylene and polyurethane. And of course, that reflects that there are a diminish of the electronic transport, or because the gap that electrons have to jump is a little higher than the other polymers. Well, we complete the computational method, extrapolate the microscopic behavior. In order to complete this microscopic behavior of the conductivity, we made a stochastic simulation to emulate the experimental situation as accurately as possible. The first part was at the position, a random deposition of graphene nanoparticles on the polymer, making a Metropolis Monte Carlo simulation. Here is a video. In this video, as you can see, is the random deposition over the matrix. the polymer matrix. The second part, in a minute is going to start the second part. The second part is the formation of graphene clusters over the polymer matrix. In this second part, we incorporate the internal tensions. Here is the second part. Here is the creation of clusters. We incorporate, as I already mentioned, the tensions, the internal tensions obtained from the DFT calculations and the quantum effects. Here we put that the graphene nanoparticles are placed in the graphene, in the polymer, in a parallel position. The third part of the simulation was used with a phase type distribution function. Here is the distribution function. And it was used to obtain the transmission probabilities of the electrons. With the transmission probabilities, we use Landauer's conductance theory to obtain the conductance. And in fact, if we have the conductance, the conductivity is directly obtained. Well, several things to agree in the third part. The third part was very complete and a little more complex than the first and second part of the computational method in the microscopic point of view. We used in the simulation a potential described by this equation. This equation was obtained by us, is not reported in literature, and it was obtained by a series of a power series of van der Waals terms. In the van der Waals terms, and the van der Waals forces in the quantum effects, it is obtained by the bracket of R power to -6, and we took this R power to -6 and expanded like a multiple expansion, and we obtained several terms. We tried every term with in the simulation and compare with the experiments, and we get only these two terms, which was a good thing for us. Only obtained two terms that describe very well the experimental setup. Well, here are a diagram of the third part, in which here is the thermalized section, and in the middle part it was the paths created for measure the transition probability. Several things to say. Well, first, and I already I forgot to mention, all the calculations are computed at room temperature, and in general, the percolation phenomenon can be described by several models that are very popular in literature. For example, limit percolation theory is one of the most popular, has gained popularity in the recent years, as it can be used to describe electronic transport in materials and polymers. However, this model starts from taking an infinite networks. This is the network from here. Limit percolation theory uses an infinite network, where the vertices have an occupation probability given by Bernoulli distribution. So the result of this model depends only on the shape of the system and not on the material. This is one issue of this limit percolation theory. In literature, there are several modifications that people made to improve the limit percolation theory. but this modification cannot guarantee the correct description of the percolation phenomena. For example, if the trajectory or a path is changed, the electrons do not imply that percolations occur. Maybe the electrons never reach the other side. On the other hand, other popular methodologies use the transmission coefficient from green function are used, for example, tie binding or green method or others. No? And these methods assume elastic electrons, periodic systems, zero temperature, and in some methods, they use systems with high electric conductivity. However, we consider that for our system, these approximations are no longer valid. Therefore, we develop a code that will take the details in account. The purpose is, oh yeah, okay. Sorry. I obtained a message from Zoom, but everything is okay. We have this method with our code to incorporate these elements of the polymer systems, polymer graphene and nanoparticles. We have a we put very attention in the inelasticities of the electrons, room temperatures, quantum effect as non-covalent interactions that we observe that are very important for these materials, and the radius of actions. And for this, we use the last passenger theory, which is more flexible because it applies to finite networks and allows the immediate introduction to the formation and the all issues and things observed from the absorption phenomena. All the nodes are considered as random variables, are not Bernoulli probabilities like other theory. And this is led us to introduce the inclusion of the materials in the equations very easy. Well, continue with the transition of the quantum simulation and the macroscopic simulation. It is well known that in elastic theory, for example, if you see what is in elastic theory, when the formation is induced in a body, the distribution of the molecules is changed and the body leaves its original state of equilibrium. New forces appears and tend to bring the body to a new equilibrium state. And the equilibrium state would be in this new molecular configuration. This induces forces and internal stresses and occur to the interaction forces between molecules or atoms. In particular, these internal stresses are due to the non-covalent interactions as the PP stacking and the CH/P stacking. In general, in a traditional macroscopic perspective, the action radius is zero, is considered as zero, but it must be quantified in these regimens because we are already seeing that the quantum effects are important and the distance in which we are observed the contribution of the absorption are very low. To quantify precisely, we use DFT, as already mentioned, which tell us precisely how the atomic distribution of the body occurs under these internal stresses due to the PP stacking and the CH/P stacking, the non-covalent interactions. For measure the deformation of these materials, we choose a coordinate system which has the origin at the center of the graphene surface, and the Z-axis containing the normal vector of the surface, which go out of the screen. When the polymer interacts with the graphene, carbon atoms can be pushed down, giving us a negative z-axis, or pull up in the positive part. So the action radius is the distance between the maximum and the minimum height near the polymer, and directly reflects the internal tensions induced by the polymer graphene interactions. Here in this table, we are showing the action radius, and also here are the percolation threshold obtained by us in these calculations, and the comparison with experimental previous papers or manuscript reported in literature. As you can see, our theory with the last passenger percolation theory is very well. We predict the percolation threshold, this critical point, with very good precision. The worst precision of our method, it was in PET with a 7%, and the best calculation, it was polypropylene and graphene with 0.3 error percent. Here is the things or the papers we use to obtain these values. Well, according to the potential equation, we, as already mentioned, we have two behaviors. Well, first of describe this plot, I want to show you these simulations, these data obtained by the simulations. As you can see, here is it was like proper Monte Carlo simulations. It was an experimental, a computational experiment in which we simulate the incorporation of the nanoparticles little by little, and then we reach the percolation threshold, and here is the change drastically of the behavior. Here is an isolating behavior, and here comes the conductor behavior. So we transform with these materials from, for example, PS polymer to a conductive polymer, from isolating to conductor. And here we observe that the percolation threshold for PS is 10.13, for PET 12.84, for PEC 16.05, for polypropylene and graphene nanocomposites. The percolation threshold was 18.25. And for polyurethane graphene was 22.17. Very, very bad percolation threshold for this kind of materials. Well, I am talking about this figure. It was several things to mention here. According to the potential equation that I already present here, we have two behaviors, right? R, or distance, power to -6, and distance power to -12. And this behavior was observed as the difference of the PP stacking and the CHP stacking. Here are the behavior of of the electronic transfer mechanism via a dispersion force of R power -6. And here is the other behavior, the CHP stacking with R -12. What we observe from this and from the simulation, first of all, we observe that the electron transfer mechanism via the R power -6, indicating that the electrons find a larger mean free path to promote electronic transport, accelerating behavior change from insulating material to conductor. Therefore, the percolation threshold comes with a percentage much lower than expected. So as I already mentioned, the expected percolation threshold, it was for 50%, but we obtained 10% of nanoparticles. This accelerating is indicating is direct a consequence of the PP stacking and the action radius, which means that this PP stacking accelerate the electronic transport, making that the electrons always find a path, a viable path to get transport from one lead to another lead. For the other behavior, for the linear polymers, the system with dominant short-range terms, which are described by R power -12, which are these, the polypropylene and polyurethane graphene. The action radius is small due to the CHP stacking is not so good for convert or for creating this path. The nanofillers have a weak interactions with the polymers, so the electrons are transported locally. This is the big difference. The main free path of the electron is short, producing low electronic transport compared with the other systems studied here. So we have to incorporate a large quantity of graphene nanoparticles to change the behavior from insulating to conductor. Additionally, we find a relationship between the action radius and the maximum conductivity. Here is the linear relationship between the action radius and the conductivity. And it displays a tight tendency. Polymers with aromatic rings have a higher electronic conductivity than linear polymers. I think I have just a little time. Is right? Is that right? I have.
We are 3 minutes ahead your time, but just you can take a couple of minutes if you want.
Thank you very much. So I'm going to make the conclusions very fast. Sorry for the delay. Well, for the conclusions, for this study, we proved that quantum effects are crucial to understanding the acceleration of the behavior change from isolating to conductor materials when graphene nanoparticles are embedded gradually on the polymer matrix. The quantum effects that mainly affect this behavior are the non-covalent interactions, as I already mentioned. These non-covalent interactions actually specifically are PP stacking and CH/P stacking. To test our hypothesis, we perform a computational simulation in which graphene nanoparticles are embedded at room temperature in several popular polymer matrix, PS, PET, PEC, polypropylene, and polyurethane. About the non-covalent interactions, these interactions were characterized in detail with an AB ab initio framework, and then they were included in a Monte Carlo simulation. The electronic transport is simulating using a phase-tab distribution with a stochastic percolation theory and Landauer formulation. The electronic conductivity of the system was successfully reproduced in strong agreement with experimental results. We also proved that the stochastic percolation theory with a phase-time distribution is a more appropriate tool because it can incorporate more details than other models, such as room temperature and the non-covalent interaction, which means that it's very better than scattering matrix or tie binding or other percolations distributions. Polymer with aromatic rings in their structure are more compatible with graphene nanoparticles to maximize the conductivity due to the PP stacking that increase the transport of electrons from graphene to polymer and vice versa. For polymers with linear structure, the non-covalent interaction are presently mainly by the CH/P stacking. Electronic transport is still promoted, although the electrons are not that accelerate compared with the aromatic polymers. It was observed that the non-covalent interactions dominate the electronic transport mechanism and promote electrons to be transferred efficiently and diminish the HOMO-LUMO gap. Also, the non-covalent interaction increases the deformation of the nanocomposites. The systems that present a more significant deformation have a higher structural coupling. These are the systems that have the cycling rings and higher absorption energy. We have the aspect ratio as the deformation radius because it characterizes the neighborhood in which the non-polymer interaction are predominant with the microscopic properties. This deformation, as already mentioned, was incorporated in Monte Carlo simulation as the aspect ratio, which is very common to calculate or estimate an aspect ratio, but we don't estimate easily. We estimate with the ab initio simulation. Well, the average error of our simulation is around 3%, especially for systems with predominant short-range ray interaction. Our simulations are very good. With this, I want to thank you your attention, and I here for any question and comments that you have. Thank you very much.
Thank you, Roxana, for your talk. So we have a few minutes for a couple of questions from the audience. Please, if you have any question, please raise your virtual hand. So, yes, we have a question from Julio. Please, Julio, go ahead.
Hi, Roxana. Thank you so much for your presentation. Really interesting. I have a couple of, well, several questions, but maybe we don't have time to,
Okay.
for longer time. The first one is, so the idea is to increase the gap, no, including different kind of polymers. Have you tried to study?
Diminish the gap.
Okay. Try to study to put like I mean in like a sandwich or the graphene instead of to have just like the substrate. What is the effect to put like the one graphene polymers and another graphene?
This would be amazing. It's I think that this is the next step to the simulations. At the moment, we only put in one side, but could be very interesting. We are thinking in bidimensional materials in which we have these layers, but we have to extrapolate to be three-dimensional materials also. Thank you for the suggestion.
Yeah. So the other question is, well, because I lost a little bit respect one of the figures that you're showing. Could you go to the results, maybe back three more. Yeah, it's the 10 exactly. But in this case, the graphene is completely plain. But in the left part, looks like you have a curvature. I mean, did you try to study like in nanotubes? I mean, nanotubes made by graphene?
Yes, nanotubes are very interesting for this kind of materials because present a lower percolation threshold, a lower critical point. And actually they are favorite for industry, make these simulations or these experiment with nanotubes. And I think that you point a very well issue or a very well thing that the rugosity is important. I mean, I think could be important for the transport properties. I don't see in literature, as far as I know, something about it, but it could be something interesting to study. About the carbon nanotubes, there are a lot interesting. We begin starting this project because this Swiss company talked with Professor Campagne and asked the investigation, the research for graphene nanoparticles. And they expect different results from carbon nanotubes to graphene nanoparticles. Even, and they expect a better mechanical mechanical properties, a better behavior. This is the issue, because with carbon nanotubes, they have a very well electronic transport properties, very well. They actually have a percolation threshold even of 6% of nanotubes, but the mechanical properties are not so good. So industry is very interesting in improve these materials, and the thing was with graphene, it could be improved. It improved a little, but not so good to get Young's models of graphene. No? There's a lot of work to do there.
Okay. And finally, by summary, which polymer do you think it's of all of polymers that you study, it's better comparing the, I mean, the gap, the conductivity, and everything that you study? Which polymer do you prefer in order to imagine that you want to make
to create
a material with for maybe possible application, no? Technological application?
I think polypropylene by far, because for the mechanical properties, combine a very low percolation threshold and have very well mechanical properties in comparison with the others.
And I guess it's cheaper.
And it's cheaper, right?
Yes,
well, this is my my first guess.
Okay, thank you so much, Rosanna.
No, thank you.
Okay, so if there is another question from the audience, please raise your hand. Well, if not, so since we are a little off the schedule, maybe we should continue. So thank you, Roxana.
Thank you for the invitation, for the great moment that I had.
Thank you. So our next invited speaker is Carmen Moraila. Please welcome, Carmen.
Hi, good morning.
Good morning. So you can, I think you can present your slides. Check. Yes. Okay. Yes. So we have Carmen Moraila from the DCI, la División de Ciencias e Ingenierías in León, University of Guanajuato. She's going to talk about applied physics, connecting physics and engineering for practical purposes. So thank you, Carmen, and your your mic is not yours.
Thank you, Gabriel. And first of all, I would like to thank to the committee of this conference for inviting me to this to give this talk to present my work and my collaborators' work. I turned off the video because I have some problems with the internet. So I'm going to start. My talk is titled Applied Physics, Connecting Physics and Engineering for Practical Purposes. Applied physics is a generic term used to describe the part of physics that is particularly interested in the use of technologies to solve practical problems. Okay, no. So in this talk, I'm going to talk about the role of the red blood cells electrical charge to diagnose diseases as a low resource technique. And after that, I will introduce the study of promising graphene derived materials such as graphene oxide, reduced graphene oxide, and laser-induced graphene for the use in flexible electronic devices for biomedical applications. And I'm going to start talking about drying droplets. Everybody has seen how a coffee drop evaporates on your table. After all liquid has evaporated, we can observe a characteristic ring formation formed by the coffee particles. When a colloidal drop is evaporating, an outward flow is created in order to conserve mass at the triple contact line. This flow carries particles out to the interface. On the contact line, we can observe some interesting phenomena, such as particle segregation by size. And in the image, we can see different cells of different sizes at the contact line. We can see in blue color, anti-mouse antibodies, the red blood cells, and some bacteria. They have different sizes and they can be segregated at the contact line. This is one of the phenomena that I'm going to talk. Taking advantage of the different morphologies formed after complex fluid evaporation, several applications have been developed. One example is the drying morphology as rapid medical diagnostics. In the image, we can observe different drying morphologies of biological fluid. The first is of a healthy patient, and the other belongs to patients with different health diseases. In this way, we can study the different diseases, for example, virus, cancer, or high prevalence diseases. But what is behind complex fluids evaporation? When we have colloidal suspension under evaporation, many phenomena can occur, such as the effect of Marangoni flow, where a gradient tension is created in order to suppress coffee drop effect. Particle segregation by size, as I mentioned before. The effect of particle-particle electrostatic interactions. For example, in this figure, I present different particle-particle electrostatic interaction using polystyrene particles, silica particles, and titanium particles, where the electrical behavior of this particle has been changed by changing the pH media. And we can observe the different morphologies formed after evaporation. And another phenomena that we can observe under free evaporation, it's in this video. I'm going to make it faster in order to see. This is a free evaporation phenomena in a silica particle droplet. And we can see at the end, as a result of the increasing of particle concentration, we can see, for example, that this type of experiment cannot be standardized. In 1997, it was established by Deegan and collaborators that the main mechanism for particle deposition by drop drying is contact line pinning, evaporation from the edge of the drop. But some years ago, we studied the effect of wettability properties of substrate on particle deposition. We studied the effect of contact angle hysteresis in particle deposits by varying pinning time of contact line. We changed the contact angle hysteresis, increasing or decreasing the pinning time, and we can obtain solid accumulation and create this self-pinning or spontaneous sticky behavior forming periodical patterns. We also studied the effect of the receding contact angle, forming a wedge-shaped region, forming a geometric constraint, and in this way we can accumulate different quantity of particles. And the evaporation driving convective flow, changing the receding contact angle, because when we vary the receding contact angle, we can tune the evaporation flux, because the receding contact angle is strongly related with the outer or the strength of the flow that carries particles to the interface. If we reduce the receding contact angle, then the outward flow is going to increase for hydrophilic droplets. As fact, low contact angle increase the diverging evaporation rate along the contact line. During my PhD and postdoctoral stages at the University of Granada in Spain, we studied the main mechanisms responsible on different morphologies formation after colloidal drop evaporation. Here I show you some papers where we present our results. For example, we vary the role of the electrostatic double layer interactions in the formation of nanoparticle ring deposits at driving receding contact angle. In this paper, we just change the electrostatic double layer interaction particle-particle. Then we studied the variation on pinning time of the driving receiving contact lines. We study the strip-like patterns to a particular film using driving evaporating meniscule. We change the morphology of the contact line to evaporating meniscule instead of a droplet. We count the in-plane particle counting at the contact line evaporation using laser confocal microscopy, and we count particle per particle going to the contact line, not along all the droplet, just by areas. But we can observe the effect of the particle electrical charge on the final morphology of the droplet. We study as well the impact of the collective diffusion of charged nanoparticles in the convective capillary deposition directed by the receiving contact lines. The particle segregation at contact lines of evaporating colloidal drops, and the influence of the substrate wettability and the particle charge mass rates. After all the results presented, we conclude that the formation of the different morphologies obtained after colloidal drop evaporation is ruled in order of importance by the following effects. The effect, first of all, the effect of the particle specificity, the wettability of the particle, the effect of particle electrical charge, the segregation of particle phase size, and finally, the substrate wettability. And now, we want to use the results for our applications such as drying complex fluids as a low resource technique for medical diagnostics. As I told you before, one application of this is the rapid medical diagnostics. And the image, you can see the different states of a healthy, the first droplet is a healthy person survey, and the other three droplets are different diseases. And you can observe the different morphologies obtained after evaporation. In this image, I showed you the blood drops for, again, for different disease, and just in the blood drops are diseases that affects especially the blood drops. And another kind of disease that can be studied is the virus, such as malaria. But we are especially interested in the effect of particle electrical charge. So, first of all, I'm going to talk about the blood. The components of the blood can be divided as the blood cells, sorry, and the plasma. The blood components are plasma and cell blood, sorry, and in the plasma, plasma is composed by water, ions, proteins, and nutrients, and many other things. And the cell bloods are the white blood cells, the red blood cells, and the platelets. They are different in size and morphology, but we can estimate some behavior of these cells just as this taken as if they were spherical. But it's very important to this study that the different sizes presented in the cellular components, the blood cells, sorry. To study the electrical properties of the blood cells, we use a zeta-meter device when an external electrical field is created in order to move the colloids. The velocity is calculated by tracking particles. The particle velocity is related with electrophoretic mobility, and using an approximation, it could be a Smoluchowski or Debye-Hacker, the zeta potential can be reduced. Our hypothesis is that the electrical properties of blood cells vary when some blood alterations that affect blood cells is present. If our hypothesis is correct, then differences in drying morphology will be present when a disease of this type is presented. This way, the title, Morphology Study of Drying Complex Fluids, a low resource techniques for medical diagnostics, is justified. Some blood diseases that can be studied after desiccation morphology are diabetes. We are interested in diabetes mellitus, hyperlipidemias, and virus. About diabetes, 1 in 11 adults have diabetes. According to International Diabetes Federation, 10% of global health expenditure is spent on diabetes. Over 3 in 4 people with diabetes live in low and middle income countries. 1 in 2 adults with diabetes are undiagnosed. 1 in 13 adults have impaired glucose tolerance. 1 in 6 live births are affected by hyperglycemia and in pregnancy. In this graph, I present you the percentage of total health spending allocated to diabetes per region. Africa, Europe, Middle East and North Africa, North America and Caribbean, South and Central America, and Southeast Asia. I present here the top 5 countries for number of people with diabetes. United States in the region of North America and Caribbean. It's the first United States of America, Mexico in the second place, and Canada, Haiti, and Jamaica. In Mexico, almost 5 million persons with diabetes are undiagnosed. This fact took importance when COVID-19 emerged. Many deaths from COVID were observed due to complications resulting from diabetes. Many people did not know they were diabetic, so they had complications. But it's about 5 million. So this number is very important. For diagnosis, according to World Health Organization, the diagnostic is the controls are blood glucose control, particularly in the diabetes type 1. People with type 1 diabetes require insulin. People with type 2 diabetes can be treated with oral medication, but may also require insulin, blood pressure control, and food care. The World Health Organization aims to stimulate and support the adoption of effective measures for the surveillance, prevention, and control of diabetes and its complications, particularly in low and middle income countries. Provide, so one of the recommendations is provide scientific guidelines for the prevention of major non-communicable disease, including diabetes, develops norms and standards for diabetes diagnosis and care, builds awareness on the global epidemic of diabetes, and conducts of diabetes and its risk factors. So in this work, I'm going to show you some preliminary experiments that we made, but just before COVID. First of all, we studied the electrical properties of red blood cells in men, just men. We choose one non-contagious disease, and we divide the experiment in two groups. The first group from 20 to 29 years old, the group 2 from 38 to 58 years old, and divided by health condition, healthy or non-healthy. The non-healthy person is high cholesterol. They have high cholesterol levels for both groups. As preliminary results, I present you the set of potential measurements made for healthy men of the first group, non-healthy men of the first group, healthy men of the group 2, the non-healthy men, the group 2, and the non-healthy men, the group 2, but older. And in all cases, as a preliminary conclusions, we observed that patients with high cholesterol level in blood presented higher zeta potential value of red blood cells compared with patients with normal cholesterol level in blood. In 2019, Bianchetti et al. Studied the membrane composition of red blood cells in presence of cholesterol, and they found that cholesterol and diabetes type 2 are related. Cholesterol is deposited in red blood cells membrane, and red blood cells membrane is modified in presence of high cholesterol level. So this can be an indicator of results that cholesterol is attaching to the cell membrane and is changing the surface electrical potential, the zeta potential. So we plan these more experiments, but for the experiments, we had one group on age from 25 to 75 years old. We divide into groups: the reference group with normal values of hepatic biometry, blood chemistry, in blood chemistry, total cholesterol, triglycerides, and glucose. And group 2, non-healthy, non-normal values of hepatic biometry and blood chemistry. Again, I'm going to present you preliminary results because we start with the sampling of patients, but because of COVID-19 with pandemic situation, then we continue making sampling after vaccines, and we restart the sampling this September 2021. With group 1, we could characterize the red blood cells electrical properties, electrophoretic mobility values, and as you observe, the electrophoretic mobility values are on the same range and does not change with sex or age. And the results of group 2 the electrophoretic mobility values increase with high cholesterol levels. For example, if you observe in red, the high cholesterol levels, we can observe an increment on the electrophoretic mobility. This, again, as I tell you, I'm telling you that they are preliminary results because of we just restart the sampling of the patients, and it's very complicated because I want to remind you that the comorbidities are especially dangerous with COVID-19. So we need to be very careful with this type of patients. So we just have these preliminary results. Patients with high cholesterol level in blood presented, again, higher electrophoretic mobility value of red blood cells compared with patients with normal cholesterol level in blood. But we need to continue the sampling in order to make better conclusions. And at the beginning of the talk, I present you the effect of the particle-particle electrostatic interaction on the final morphology of drying droplets. When the electrical particle charge changes, the morphology changes totally. For example, in the image, you observe, for example, the silica particles. At pH 2, they have low electrical charge, and at pH 9, they have high electrical charge. The repulsion electrical repulsion particle is high at pH 9, and the morphology totally changes. So, if when diabetes or high cholesterol level is presented in blood, and the cholesterol is attaching to the red membrane of the red blood cells, then the surface of the electrical charge of the surface of the red blood cells appears that changes. If the red blood cells charge, electrical charge changes, then the morphology is going to change. So the morphology, we can talk about a morphologic study of drying droplets complex fluids as a low resource technique for medical diagnostic, especially of diabetes. And as further work, we need to increase the number of patients with high cholesterol level, and we want to study the rheological properties of red blood cells membrane by means of typical research experiments. But during pandemics, we could not sample patients or even work at the laboratory. I think like in every part of Mexico. In May 2021, after vaccines, we still cannot sample patients, but we can work at lab. So this way, we try to emulate diseases using polymeric particles of same size compared with blood cells. For this purpose, we use polystyrene particles of 2, 7, and 12 microns in order to emulate platelets, white blood cells, and red blood cells. The electrical properties can be modified by means of pH, as I showed you in this graph, the electrophoretic mobility versus the pH. As the red blood cell experiments for measuring zeta potential, we dilute the red blood cells on PBA solution. So we dilute as well the PS particles in order to find the electrophoretic mobility of polystyrene particles with values close to the red blood cells electrophoretic mobility values. And we found that at pH 7 and concentration of 0.001x of PBX, the electrophoretic mobility is similar to the electrophoretic mobility of the red blood cells. This way, we can emulate in size and electrical behavior the red blood cells with at these conditions. So trying to emulate the increase of cholesterol in blood, we made experiments adding cholesterol to this particle suspension, increasing the concentration of cholesterol. And we obtained that the electrophoretic mobility measurements values, increase with the concentration of cholesterol. But all these experiments were carried out before the experiments using samples with red blood cells of real patients. And as you can see, the results are similar, not in value, but just in behavior. That cholesterol increase the electrophoretic mobility of particles with the same size of red blood cells. And another disease that we are interested is to study the virus, especially not COVID, just dengue virus, because in Mexico, especially in tropical regions, we have this virus, this disease every year. And almost half a year in, for example, at the north of Mexico, we have many deaths occasioned by dengue virus. In this case, first of all, I want to remind you that the blood cells have different sizes. They are very different. Platelets from 2 to 3 microns, to white blood cells from 12 to 15 microns. And when dengue virus appears, a very important decrease in the number of platelets is presented. So we made an artificial decrease of platelets concentration. In the first image, the platelets, as is expected, the platelets, which are the smallest, go to the interface, forming a ring at the contact line. Then we decrease the platelets concentration at just removing the platelets on blood, and we observe how this ring decreases in width. We continue reducing the platelets concentration, and the ring made thinner, and we remove all platelets, and we don't have this outer ring formed by platelets. So if we study the width of this ring, we can study if we study the width of the outer ring of the blood droplets, we can have an idea of the quantity of platelets presented on blood. So again, we can emulate this kind of diseases, just changing the number or varying the number of the particles. We use a white light confocal microscope, and for example, and we made we studied the profile morphology of droplets using the polystyrene particles with the same size of the blood cells, sorry. I present you here the profile. Just PS particles of 7 microns, the ones that emulate the red blood cells. And this is the topography. Now we made experiments with the other sizes of particles, 2, 7, and 12 microns, and here are the topographies. as expected again, is in the 2 microns, we observe a ring, an outer ring of composed by these particles, these smallest particles, the 7 and the 12 microns, and the profiles obtained. Now, if we try to emulate, for example, dengue virus, where a decrement of platelets is presented, we just remove the quantity of platelets on the droplet. For example, in figure A, we observe a droplet with concentrations that emulate a healthy person with the number of particles of 2, 7, and 12 microns. And in figures B, C, and D, we decrease the quantity of platelets. And we observe how the outer ring changes. And the profile morphology of the confocal microscope confirms this reduction on the ring, on the morphology of the outer ring. So now I'm going to talk about another collaboration with the University of Granada, which is laser-induced graphene. Sorry. Graphene is a one-atomic layer of carbon atoms arranged in a hexagonal lattice. It is the building block of graphite. It is the thinnest material known to man at one atom thick, and also incredibly strong, about 200 times stronger than steel. It is an excellent conductor of heat and electricity and has interesting light absorption abilities. Recently, graphene also emerged as key player for the development of flexible electronic devices. Factors such as high volume manufacturing, reliability, and performance per cost difficult the cost-effective circuit integration of these materials, and therefore the wide commercialization of electronic devices based on them. Alternative materials and fabrication technologies that allow the inexpensive mass production of sensor and electronic devices over flexible substrate. The unique physical, electronical, optical, mechanical, and chemical properties of these 2D materials make it a perfect candidate to cause a disruption in the field of flexible electronic, as well as in many other areas of technology. Graphene oxide has become of high interest within the graphene research community, given that it can be easily synthesized from the chemical oxidation and sonic exfoliation of bare graphite powder. In this context, the study of promising graphene derivative materials such as graphene oxide, reduced graphene oxide, and laser-induced graphene for the use in flexible application devices acquired relevance. The lesser reduction, the lesser reduction of oxide graphene offered the advantage of being able to obtain reduced graphene oxide patterns in various geometries with micrometer resolution without the use of lithography mask, environmental friendly and is able to modulate the electrical conductivity of the resulting reduced graphene oxide sheets. The laser synthesis of graphene-based nanomaterials open up a wide range of possibilities for the development of flexible electronic devices, given its suitability of a straightforward synthesis in a scalable approach. This work is focused in the study of a cost-effective technique for the synthesis of rough graphene-based electrodes and its optimization. So I'm going to present you here a work titled Laser Synthesized Nanography Based Electrodes for Flexible Supercapacitors. For this work, we use two different fabrication processes. laser-reduced graphene oxide, and laser-induced graphene. For the first fabrication process, here I show you the steps that we follow in order to obtain the laser-reduced graphene oxide. We use a PET film of 160 microns. The graphene oxide we deposit the graphene oxide onto the PET substrate. Then we made the laser scribing process to reduce the graphene oxide. We use silver electrical printed on each electrode. And finally, we use the PVA electrolyte drop casted on top of the interdigital electrode structure. And to obtain laser-induced graphene, we use a precursor such as Kapton polyimide film of 75 microns, and we follow the same steps that the one in the PET film. We try two different lasers, the CO2 and the UV. And I'm going to show you the results of the structural analysis. First of all, the sheet resistance. With the laser of CO2 for the different materials, first of all, we made the optimization for the different laser beams, and we changed the laser speed, the laser power, and I show you here in table the sheet resistance per square. We made Raman spectra, and Raman and XPS confirmed that the graphene derivate nature of this material. XPS analysis shows that the ablated surfaces are mainly composed of carbon and oxygen percent. This means that they present carbon-oxygen groups, and the laser treatment lead to a drastic increase in the original CO carbon-oxygen ratio. We observe that the higher ratio of carbon and oxygen is with the laser of CO2 for both materials. Once all 4 different materials were analyzed from a structural point of view, we studied the electrochemical performance as electrodes for flexible capacitors. For the first, we performed cyclic voltammetry experiments with a potential window of 1 volt from minus 0.5 to 0.5 volts. And I present you the results for different materials and treatment and lasers. Apart from reduced graphene oxide synthesized with UV laser, the curves maintain a highly symmetric quasi-rectangular shape over the increasing scan rates, indicating a good reversible electrochemical double layer capacitor behavior and a fast charge propagation with the electron. But are they flexible? In figures, we can see how these devices are capable of maintaining their electrochemical performance under different bend conditions without significant changes to the specific capacitance, because here I present here are the results for outer band and inner band for the different treatments and materials and lasers, sorry. And we don't have we have that they maintain the electrochemical performance under different bend conditions. The radius bend was 1.25 centimeters. So the answer is yes, they are flexible. We also test the cyclability of the different electrodes by increasing the number of current voltage cycles at 100 millivolts per second. As shown, capacitors are able to retain their capacitance. And in applications where the size is not a constraint, it is possible to combine different supercapacitors to increase either current delivered or operation voltage. And in the figure at the right present different series parallel configurations. And we can see that if two capacitors are combined in series, they operate at double voltage without compromising their performance. And if they are connected in parallel, the equivalent capacitance is twice the capacitance of a single device. So, thank you for your attention. If you have any question.
Thank you, Carmen. Thank you for your presentation. So if we have, if somebody in the audience have a question, please raise your hand. Or in the meanwhile, maybe I can ask you a little question.
Okay.
If we can go back to your 24th slide, I think it's the 24th. Look,
About
me, it's about the stain, that one, the dried blood.
Mm-hmm.
So in this one this is a blood from a patient disease, from a disease, right?
no, not this one. No, this is
Yeah.
with the normal levels in blood, and we just decrease the number of platelets artificially. We remove the platelets just to emulate some virus like dengue.
Okay, probably, and it has virus in it.
No,
Okay.
no. We
Just
just try to emulate that when dengue virus appears with the number or just the reduction of number of platelets in blood.
Okay.
Yes.
So it has more red blood cells than it usually has, right?
No,
I mean,
no.
concentration. I mean, in the ratio, let's say the ratio.
Yes.
Because it looks interesting to me because it looks like it forms crystals. Right, and it's okay. I was going to ask you a question, but it is interesting because when you have high concentration and more monodisperse, let's say particles in it forms crystals, right? So these fractures look like that, exactly like that. So I probably didn't pay attention on your explanation.
No.
So, yeah, but it looks like that. And also another question. Well, maybe you explain that, or I mean, your studies are mainly in the electrostatic interactions, right? Or this
Yes.
is
Just
main,
electrostatic interaction.
yeah. When you have and that one, no, the other one, the image. I mean, it's quite easier to see the spots. That one, yeah. You have normal in the top right. Yes, it's a normal patient, and then you have different degrees of cholesterol, right? Of cholesterol levels. So it is also interesting to me because I mean, probably in the normal you have an equilibrium, or in your studies are mainly the the amount of electrostatics that makes the blood is suspended or is in solution or something, right? And then you disrupt this balance and you start making these aggregates, right? And then you can see these fractures on your drying process. Is that correct?
Yes, but in these cases, they are just red blood cells. But when just red blood cells, yes. Yes, we are interested.
Not white blood cells, not
Exactly. Yes.
Ah, okay.
Red blood cells.
Also is interesting because in the normal, it doesn't make cracks.
Yes.
Okay. So the thing is, probably, I mean, my question, I just was wondering if the concentration of these red blood cells makes that how to say, appears or promotes another kind of interaction, like steric interactions. Is that possible? Or these are very low interactions that is negligible.
Oh, okay. Maybe, but because when present high cholesterol levels, as in this, for example, with these are not my results, but they found that cholesterol aggregates to the cell membrane, so to the surface of the cell. So the interactions between surfaces can be changed. We just obtained that the zeta potential or the electrostatic surface on the cell changes due to cholesterol, but we don't know why. We didn't know why, but now we found this result that they prove that when you have cholesterol, they change the polarity of the membrane and even the viscosity of the membrane. So they totally change the surface of the cell. So many interactions can be possible there.
Okay, I see.
We're just studying the electrostatic interaction or how the electrical charge of these red blood cells changes. But we want to study.
Mainly electrostatic is the greatest interaction. I mean the higher magnitude interaction, right?
Yes.
Okay. So, is there a question in the audience? I give you time to think about it. Maybe there is no. Okay, no, we don't have no more questions probably. So, well, we are just in time for the coffee break. I think a little bit more time, but if you don't have more questions, so probably we can go to the discussions. I mean, if there is a Paco or Eric, are we going to open the other?
Hi, Gabriel. So now is the coffee break, no?
And now is the coffee break, but sometimes
and we will continue at 11:20, I think.
Yes. I will
pause. So this is the brief outline of my talk. First, I will introduce the system, and then the research work has been divided into 3 parts. In the first 2 parts, I will discuss about the synchronizing behavior of camphor rotors. And in the third part, I'll talk about chimera-like states. As I go along, I will introduce these terms as they come along in the presentation. So as has been nicely talked about in this conference multiple times, collective dynamics is the behavior of interacting autonomous units. So these autonomous units can be living or non-living. And the interaction of these autonomous units shows the ability of an ensemble to show a different dynamics from the individual units. The interaction among the units are often of linear or non-linear nature. In the previous talks, these interactions or the collective dynamics has been talked in the lieu of active matter. Here I will give a little different prospect. I will talk about the non-linear aspects of self-propelled routers. So in non-linear community, we typically portray an autonomous unit by a self-sustained oscillator, and the collective dynamics of these self-sustained oscillators can lead to a rich variety of phenomena, few of which I have listed here. In the interest of this talk, I will give a brief introduction about the synchronization and chimera states. So synchronization is the rhythmical behavior of two or more coupled oscillators. And the first fingerprint of synchronization was given by Huygens in 1665, where he observed that when the two clocks which are hung from the same wooden beam, they showed antiphase synchronization. And to give you a visual view of how the synchronized dynamics look like, I am showing here a video where 5 metronomes are placed on a common wooden platform. I have taken this video from YouTube. And after some transient dynamics, you will see that these metronomes, they are doing this mechanical motion in unison. Also, you can hear from the audio that their motions have been in unison. This unison behavior of the coupled oscillators is what is termed as synchronization. Until now, it has been observed in a variety of systems and a wide range of scales, ranging from micro scales all the way up to planets. So then the self-propelled particles, I hope the audience here know what these are, just to give a brief introduction again. So the self-propelled particles are motile entities which moves by consuming their free energy or energy from the environment. They do not need an external source of energy for their motion. So these self-propelled particles can be living, which are bacteria, E. coli, etc. Or they can be artificially generated in the lab, for example, vibrated granular matter or nanorods. What we were interested were in the chemical active self-propelled particles. So the chemical active self-propelled particle further can be solid on a liquid or liquid on a liquid. So the solid on liquid is where this camphor system lies, which I will talk about in the coming slides. And there is liquid on liquid, where the drops move on the surface of a liquid. This kind of drop behavior has been extensively studied by my collaborator, Professor Pimienta. With this, I will briefly introduce the camphor system that we have worked on. So camphor is an organic compound which is highly soluble in ethanol. So when you put a camphor loaded disc on the water surface, it instantaneously starts to move. How we prepare this camphor disc, I will talk about in the coming slides. So this system was roughly started around 1860 by Charles Thomilson, and then the mechanism was explained by Vander Mansberg in 1869, which I will try to explain with the help of this schematic diagram. So when you put a camphor particle on the surface of water, it forms a layer around it. Any initial inhomogeneity in the distribution of this layer lead to a net surface tension gradient around the particle, and hence the acceleration of the particle towards higher surface tension, which in this case is towards my left-hand side, that is towards T1 side. So the next question is, why do we study camphor system? This is because it is easily available, easy to set up, cheap system, and this is not a dangerous system to work for an experimentalist. And although very simple to set up, this system has evolved itself into bringing about the understanding of some complex phenomena that we see in the biological systems. So Nakata and his co-worker gave a new insight to this system in 1997. And after that, it has been studied in a lot of different experimental and numerical conditions. With this, I will start with the first part where I will talk about the two camphor ribbons. So camphor ribbon is a rectangular sheet which we dip in a camphor and ethanol solution and let it dry in the air for some times. And the ethanol evaporates fast than camphor, and what is left after some time on this rectangular strip is camphor. This camphor infused strip is what we call as camphor ribbon or camphor rotor interchangeably. Now we prepare multiple such rotors and place them on the surface of water with the help of these pivots. So all these experiments are performed inside plexiglass enclosure. This is to make sure that the external air disturbance is not hindering the dynamics of the rotor. These experiments are very sensitive to the external disturbance, so one has to be very careful while performing these experiments. And then the dynamics is recorded with a GoPro camera. So this is how a single rotor perform its dynamics at the air-water interface. So the initial direction of rotation can be clockwise or anti-clockwise and is decided by the initial fluctuations. And however, during the experiment, if you want to switch the direction, that you can do with the help of external forcing. Then in this plot, I'm showing you the decay of the angular frequency of this rotor with time, which clearly indicates that the rotor has a finite lifetime on the surface of water. And after some times, when the surface tension gradient diminishes, the rotor stops. And then when we place two such rotors on the water surface at a pivot to pivot distance, these blue wires are the pivot, less than twice the length of a single ribbon, which in this presentation I will call as LC. In this setting, we were able to observe two modes of synchronization, which is co-rotating or counter-rotating. In co-rotating, both of the ribbons move in same direction, while in the counter-rotating, they move in opposite direction. And the source of coupling or the mechanism of interaction between these ribbons is the camphor layer exchange on the common water medium. Furthermore, in the experiments, we perceive that counter-rotating mode of synchrony is more robust than the co-rotating mode. And these are the proof of the synchronization, which are the phase plots. These phase plots were drawn by particle tracking of the white dots which were present on the ribbons, these white dots. And these phase plots clearly indicate that there is synchrony. So this red curve, which is for the x position of the particles, and y curve in both of the figures are for the y positions. So you can see that in the co-rotating case, both of these curves are aligned along the line of slope 1. That means there is in-phase synchrony in this case. However, in the case of counter-rotating, the x positions are in-phase lag synchronized, while the y positions are out-of-phase lag synchronized. This type of synchronization, where you have in and out simultaneously, is termed as mixed synchrony or mirror synchrony in nonlinear literature. Now I will proceed with the second part. Then after this, we were interested to know the behavior of multiple ribbon. In particularly, we started this project with an idea that if we put 3 ribbons on a triangular geometry, which we know is a frustrated geometry, would we be able to see frustrated like dynamics, the one that we typically see in antiferromagnetic spin cases? So with that aim, we again set up the experiments. The setup is same as I talked about in part 1. However, the difference is that now the number of rotors have changed and they will be placed in different geometries on the water surface. So for this part and for rest of the presentation, I will introduce this schematic representation where these blobs represent a ribbon. So now the direction of rotation of a single ribbon is redundant. What we are concerned about or interested in, what is the kind of bond that 2 ribbons are sharing? If they are sharing a co-rotating bond, we will call it positive. If they are counter-rotating, we will call it negative. This red blob means this ribbon is moving in opposite direction. So then when we place 3 ribbons on a line, one by one, we place them on the water surface, and after some transient dynamics, they end up into any of the configuration corresponding to the schematic representation. And here I'm showing you the video corresponding to the B state, where the central ribbon is moving in opposite direction. Furthermore, the C state has one more sister state, which is by the permutation and combination of this plus and negative sign. So we were able to observe multiple configurations when we have more than 2 rotors on the water surface. Then we checked this for a triangular geometry with our idea that would we be able to see frustrated like dynamics, but the answer is no. What we were able to observe again was the rotational synchronization in the multiple configurations, again in this case. Furthermore, because of the closeness of the geometry, these 2 configurations were not permitted and were not seen in the experiments. However, all the permitter configurations we observed in the experiments. Then we put 4 such rotors on the water surface on a line. And again, in this case, we were able to observe multiple configuration corresponding to these sketches I am showing you here. Then the 4 rotors were placed on a square geometry. And again, because of the closeness of the geometry, these 2 states were not observed, and we did not see them in the experiments. However, again, the multiple configurations were observed. This I'm showing corresponding to B state and C state. Then we went ahead and checked that if the disparity in the degree I mean number of nearest neighbor of the rotor will give us some other kind of collective dynamics. And for that, we chose a star geometry where the central ribbon has a degree of 4 and the peripheral one has a degree of 1. So with this disparity, even with this disparity, we were not able to observe any other dynamics, but we again saw rotational synchronization of camphor ribbon in the case of multiple configurations, which are shown over here. So with this, I will come to the next part where I'll talk about chimera-like states. I think this is a new term for the audience here. So I'll briefly introduce what chimera states are. These are spatiotemporal pattern in an ensemble of identical oscillators, which are described as coexisting synchronized and unsynchronized group. This field came into limelight in 2002 with Kuramoto and Batoktok discovery. And then later on, these states were dubbed as chimera states. This name chimera is inspired from Greek mythology character whose body composed of 3 animal bodies. So after this numerical discovery, it took roughly around a decade for the first experimental verification of these states by 2 groups on BZ oscillators and in the case of liquid crystals. So then we were interested to know that what would be the minimum number of oscillators that can sustain these chimera states. For that, we placed 3 rotors on a triangular geometry. However, now in this setup, the distance between them is slightly greater than LC. Earlier, they were at a distance less than LC. And we almost double the concentration of camphor which was loaded onto the ribbons. And in this setup, we were able to see chimera-like states, which I will explain. So in these states, you will see that the first and second rotor, they are synchronized, which is nicely shown by the phase plot here. While the first and third and second and third, they are unsynchronized, which is shown again by the phase plots. So this simultaneous existence of a synchronized pair and 2 unsynchronized pair is what we call as chimera-like state in our experiments. So how much time do I have?
Sorry, I wasn't checking. I will.
Okay, so
just continue. You have enough
okay.
time. I think
Okay.
Up to 12. Then you have 20 minutes. About.
Oh. Next, we have a simulation model. In the simulation model, what we did is we consider these ribbons as point particles, and these point particles were interacting via Yukawa potential. So why Yukawa potential? Because we believe that in the vicinity where both of the ribbons are depositing camphor, there is more camphor here than it is in the outside. So then the ribbons have natural tendency to move from this common region to outward region. So that one can perceive as a repulsive interaction, and that we are mimicking through Yukawa potential. The range of this potential is decided by 1/k. And this is the force component. Furthermore, we believe that the radial component of the force is balanced by the pivot, and it's only the tangential component which is acting on the particles, and it is hindering, it is giving them the dynamics. So these are the dynamical equations which we simulated. We gave initial angular frequency and the direction of angular frequency, as well as we give initial thetas. And doing that, we were able to see co-rotating and counter-rotating mode of synchronization. So in the co-rotating mode, again, both the point particles were moving in same direction, while in the counter-rotating case, both the particles were moving in opposite. So using this model, we were able to reproduce the synchrony in both of the modes here. Now from this co-rotating to counter-rotating mode, the beauty of this model is we just change the sign of one of the initial omegas, and just by doing that, we were able to switch from one state to the another state synchronization. And these are the phase plots which I'm showing corresponding to the simulations. However, there are some differences between the simulations and the experiments. As I was talking about in the first part, where I showed that there is a decay in the angular frequency with the time, that we were not able to see in the simulation. So in the simulation, there is no decay in the angular frequency of the particles. The angular frequency is decided initially. Secondly, here you see that inside the simulation, inside these phase plots, we have filling of the data points, which was not there earlier in the experiments. This we believe is because the primitive nature of our model, where we are not considering how the switch in the direction of the particles is giving us the dynamics. So this we further rectified later. Okay, I think there is a confusion. I was told that it's a 15-minute presentation, so maybe I can. Okay. So then in the second part, we rectified our initial simulation model. We added this term, which shows the tendency of a rotor to go to its autonomous frequency. And doing that, we were able to rectify the filling inside the blobs, which is now nicely shown here in the simulation. So these are the phase plots which I'm showing you corresponding to the experimental videos that I already showed you for the 3 particles on a line. So now you can see from the phase plots here that in the case of simulations and experiments, there is a nice qualitative correlation between them. Apart from that, in the case of simulations, now we have a very nice phase plots where you have almost complete synchrony in the simulations, but there is again in phase lag synchrony in the case of multiple such rotors. Again, these are the phase plots corresponding to the 3 particles placed on a triangular geometry. And this is corresponds to the video that I already showed for plus configuration. And then for the 4 on a line, again, we were able to see simulation and experiments nicely matched in that case. So for the 4 particles on a square also, our simulation and experiments nicely matched. And same is in the case of 5 particles on a star. Then in the case of chimera-like states, we were again able to see that using this Yukawa model, which I already discussed, we were able to see chimera states again, where you can see that first and third particle, they are synchronized, while all the other particles, they are not synchronized with each other. So then in the simulation, we furthermore checked what is the frequency mismatch dependence on the emergence of chimera-like states. For that, what we did is we initially chose the rotor 1 and 2, they will be synchronized and the other ones will not be synchronized. So here you can see that for the synchronized rotors or a synchronized pair, the detuning, which is the frequency mismatch between them, should be below a threshold value. So if that is below a threshold value, you see a chimera-like state, which is shown by a red dot. And if that detuning is higher than that, a threshold value, you see a non-chimera-like state. So these non-chimera-like states can be a complete synchronized state or a complete unsynchronized state. So from that, we came to know that there has to be a minimum threshold between the frequency mismatch between the synchronized particles for the emergence of chimera-like states. So with this, I will conclude my presentation. That we were able to see coupled self-propelled camphor rotors, and we experimentally and numerically showed 2 main nonlinear behavior in these rotors, which were synchronization and chimera-like states. The synchronizations was observed for L less than LC for the 2 rotors and multiple rotors, and chimera-like states were seen at L greater than LC on a triangular geometry. Furthermore, which I have not shown in the presentation, in the case of 2 and 3 rotors placed on a triangular geometry, we were able to show that a negative bond is preferred over a positive bond. Furthermore, our numerical model using Yukawa potential was qualitatively able to reproduce synchronized and chimera-like state. With this, I will end my presentation, and I thank you everyone for attending this. I apologize that I think finishing early because there was a confusion. I was told that it's a 15-minute presentation, so I prepared accordingly. I apologize for finishing
Actually,
before
it was my
time.
mistake. Sorry, Jyoti, it was my mistake. I got confused with the program. I was looking, it was finishing at 12:10. I mean, local time.
Okay.
But yes, indeed, it was a 20 minutes talk plus questions. Okay. So
Okay.
thank you for your presentation.
Thank you.
And
Thank you.
we will open to the audience if there are questions. Yeah, we have a question. Yeah, Juan Ruben, can you ask your question, please?
Yeah, can you hear me?
Yes.
Yes, yes.
All right. Thank you, Jyoti, for your very interesting presentation. I have a question concerning the direction of rotation of your ribbons. What determines this direction? Are they chiral? Are they asymmetric? Or why do they rotate in a certain direction? This was not clear to me. Could you please explain?
Yes. So as these are symmetric particles, so you cannot, like chiral particles, you cannot initially predetermine their direction of rotation. So when you put them on water surface, their direction is decided by initial fluctuations only. Okay. So when you put it ideally in ideal scenarios, you would expect that 50% of the time they will move in clockwise direction and 50% of the time they will move in anti-clockwise direction because of their symmetric nature. However, if you have a chiral particle, you can make a comma-shaped camphor particle. And if you put that, now depending upon the chirality, you will already know if it will move in clockwise or in anti-clockwise direction. So here we do not have the idea of initial direction of rotation. Does that answer the question?
Yeah, as far as I understood, this is due to the initial condition. Once the ribbon decides its initial direction, it stays there, right?
Yes, it stays there unless you externally perturb it.
Okay.
So, for example, even a minute air disturbance, if you put on the air-water interface, can trigger the rotor in another direction. But if there is no external perturbation, it stays in the direction that is initially picked up by it.
Okay. May I ask another question? No.
Yes, yes.
Yeah. Also in your model, you said that in your model, you only consider rotation frequency, which is constant. But did you try to also somehow include the time evolution because of the decrease, the decrease in rotation you observe in experiments? Did you try to do this in your model?
No, we have not tried to do that in our model. What we were actually looking for was a qualitative match between the simulation and experiments, which even with the constant angular frequency, we were able to achieve. So we have not tried with the change, but yes, that can be tried in future. Yeah.
Okay, thank you very much.
Thank you, thank you.
Okay, thank you. So we have another question. Paco, please open your mic.
Thank you, Gabriel. Thank you, Jerry, for your really interesting talk.
Thank you.
If may, I have a couple of questions. One regarding about the question of Juan Ruben. When you put this camphor, is what they call?
Yes, camphor.
Pills in water, then this parameter LC, this distance between two camphor pills, is given. I mean, you study this distance, or you specify this distance by a systematic study. I would think in terms of at which distance you optimize this synchronization. Is that right?
Yes. If the pivot to pivot distance, the distance between these wires is less than LC, then we see synchronized dynamics. If it's slightly greater than that, as I already talked in the third part, then we were able to see chimera-like states in a triangular geometry only.
I see. So it's basically given by this hydrodynamics stress of the fluid given by this ribbon, right?
Yes. There are actually two schools which talk about the interaction. There is one school which talk about interaction in the terms of the chemical coupling between the rotor because of the exchange of camphor molecule. And then in the other school, people talk about hydrodynamic interactions. So, but in our model or in our understanding, we are not focused on the hydrodynamic part. What we were focusing on the chemical interactions between these particles. And that is why we put repulsive interactions using Yukawa potential.
I see. But it's very implicit. I mean, I think
yes,
that's what I found really interesting, because in your model is very simple, right? So you just put this Yukawa repulsion between the particles, and then one thing that maybe it would be interesting for you, I don't know what you think about it, that you start the model with a frequency that is given fixed. I mean, it's fixed. You don't put this initial condition whether the particle moves clockwise or counterclockwise randomly. You just put it clockwise, for example, no? And see their co-rotating case, no? And then you put contact clockwise and clockwise, and you see the contact rotating, no?
Right. So yeah, so that model really gives us an insight that maybe it's only the type of repulsion, for example, here through Yukawa is playing an important role here. Like I told, that people have really looked into more detailed model, in the sense that considering the flow of the liquid, and there are very nice simulation model considering this system, but even with this simplistic model, we were able to show that one can have both the synchronization and chimera states. So in that term, this simplistic model is very rich in producing the dynamics that we were looking at.
Yes. Thank you very much.
Thank you.
Thank you. And we have time for another quick question, probably. Someone has in the audience, please. Well, I think there are no more questions. Okay, thank you very much, Jyoti. It was very nice experiments.
Thank you,
Okay.
sir. Thank you.
Thank you. So
Thank
next we have well, the conclusion of this event. So please, all the organizers, please open your mics and your cameras. I think we will discuss a little bit on remarks of this version or issue, or I mean, of the 33rd conference. I think it was different as we were used to have it. I mean, this virtual event due to the pandemics. I hope next year will be, as we say, on flesh and bones. Okay, so if someone has some words to say for this conclusion, please.
Okay, so if may I say some words, so just to say that thank you for your participation in this second online version of this conference. As Gabriel said, I really hope that the next year we have different conference, more like with more physical interaction, and thank you for especially for all our contributed speakers, invited speakers, and poster presenters as well for their effort to present their work and to answer all our doubts about their works. And we will. I have received a couple of comments and suggestions for the next sessions. I mean, next versions of the conference. That this suggestion will be taken out, of course, and I think it's all. Thank you.
Thank you, Paco. Susana, you want?
Yes, I would like just to say that it was a very really success, because we have all the sessions. I was recently last week in another conference.
Dana,
and it
your
was,
volume is too low.
Many people didn't arrive to give their talks. In this case, we have a very good participation, and also, if you notice, we have a lot of women. Yes, so it was very nice to see that. Thank you.
Thanks. So, does someone else want to say some words?
Yeah.
Julio? Yes.
Yeah. You hear me? Yes.
Yes.
Yes, actually, this this meeting was special because was the second that it's in León. I mean, maybe we can get a feedback or the audience or for the invited speakers or contribute speakers in order to improve this kind of I mean the virtual sessions. Actually, maybe for the next year we can the conditions by the pandemic will be different, but maybe we can keep one of like a virtuality. I mean, some speakers can give the presentation, no, I mean, in a presential way, but others can give their presentation in a virtual way. I mean, because for some people, maybe they want to participate in the meeting, but it's difficult to travel maybe from the other country or from the other continent, but we can see that online we can take advantage, no, to discuss, to get information or to obtain I mean the knowledge, and this is a good way. I mean, we can take advantage that that the virtuality it's not completely bad. So I guess maybe we have to discuss to get options to improve for the next occasion for the next year, no, to have a hybrid version of the International Conference on Science and Technology on Complex Fluids. Thank you so much to everyone.
Okay, thank you, Julio. Yes, it's indeed, this is a good thing that we can continue doing. I mean, a hybrid scheme of the conference. It could be useful for those people that can travel, I mean, overseas or from another country. Yes. So probably there is another participation of the organizers.
Or maybe from the audience.
Yes, we can receive some comments from the attendees. Let us know.
Yes, if someone wants to participate, just.
And also between the attendees, there is a couple of professors that also want to take. From the attendees, there is a couple of professors that actually can give us a very nice feedback from the conference.
Exactly.
Yes. Just a quick comment before to give the microphone to the audience. Let me tell something about the certificates, because somebody asked me about the certificates. So we will give certificates for all the participants and attendees in the following days, right, Eric?
It depends on the video. Yeah, don't worry. Maybe the next week of the attendees, participants, invited professors will receive their certificate of participation. And the certificate includes all the authors, just in case for the poster, for example, that may require for the co-authors to actually have a feedback for it. Valeria wants to talk. Have a message from Valeria.
She wrote a message for everyone. If you want to talk. Or I may just can read it.
Yeah, okay, no, I can unmute. Can you hear me?
Yes.
Oh, good. I never used this webinar. So thank you for the organization. It was great. And I know it's a challenge to do all virtual meeting, but I see that now it's becoming the norm also in some big meetings to have a consecutive in-person and hybrid sessions. And this may be the way for next year, so that the people that are close and can make it are in the sessions, and then still you have some other sessions that are fully virtual. I think that the main challenge is to have the hybrid in which you have really people in the room and people outside at the same time. That is really difficult, but to have consecutive ones, or maybe the afternoon and the morning, something like this, it may be a way to go. And that allows many more people to participate. So, but thank you for the organization and for everyone for the talks and everything. It was great.
Thank you for your words. Yes, it encourages us to continue. So I think we wait if someone else wants to participate from the audience. Yeah. Yoti, please open your mic.
Yes, thank you everyone for the nice conference. I really enjoyed it. But I have just one suggestion. If it would be possible to put an abstract book of the poster presenter as well as the contributed talks, that will give an audience more clear picture of what they can expect from the talk or the poster presentation. So if that's the suggestion from my end.
Yeah, thank you. That's indeed a very good suggestion. I mean, we can do it for the next time.
Yeah. Thank you so much.
Yeah.
Gabriel, I don't know if there is more comments from the audience, but I also remember that just to say that we have, I don't know what to do with what I did with my camera, but yeah, so so just to tell that we have some prizes for best posters. So we thank in advance to the invited speakers and contributed speakers that are participating as jury. So I hope next week we will have the results to best posters, and yeah, we'll let you know.
The winners.
The winners, yeah.
Also for the Alexa. Yeah. Okay, well, I think that this is it. We conclude, officially conclude this issue of the International Conference of Science and Technology of Complex Fluids. So thank you, everyone. Thank you, the organizers. Thank you, the presenters, the contributed talks, the invited speakers, the posters, the attendees, everyone. Thank you for attending this conference, and see you next year, probably on Flesh and Bones. Thank you.
Yeah, put the mariachis now.
That's Eric. Eric is the
mariachis and Mexican food and everything.
Is the music guy.
And
Cheers, guys.
don't forget it. It's important.
Cheers, guys. Thank you.
Thank you.
See you to everyone, and
see you next year
to participate. We hope to see you next year.
Yes.
See you.
Bye, everyone. Bye.
Bye-bye.